Hello, this is Mr. Collier, and today we're looking at the algebra of complex numbers. Okay, so first of all, let's look at what a complex number is. It's formally defined as I squared equals -1, okay, which of course means that I equals root -1. So now we can deal with the roots of negative numbers. Okay, so in this example here, we could say this is actually root 8 root -1, so we can call this root 8I, or usually we put the I in front, I root 8. So we can simplify some negative surds like this. We can always write a surd of a negative number in terms of I. So be careful, this here, we cannot say it equals root -2 times -8, and that would be 16 equals 4, because this is a real number and these are complex numbers, right? So this step here doesn't work. If you want to simplify this, this is root 8I, and this one here is root 2I, so altogether we get root 16I, which is 4I. So this product here is actually, sorry, it's not 4I, it's 4I squared. Remember, I squared is -1, so actually it's equal to -4, okay? Alright, so complex numbers are always written in this form. They're always written as a number plus bi. So you can write a complex number like this, where we call this the real part of a plus bi is a, and the imaginary part is b. Okay, so for example, actually all the numbers we've done so far, all the real numbers are a subset of complex numbers. So all real numbers you can write as a complex number. For example, the number 2, you can write as a complex number by simply writing it as 2 plus 0i. Okay, but a number like 2 plus 1i doesn't simplify to a real number, so this is a purely complex number. All right, so let's move on here to some adding, subtracting, multiplying, dividing with complex numbers. So if we've got a couple complex numbers, these numbers here, we can add them together, and you simply add the real parts. So 4 plus 7 is 11. Then add the imaginary parts, -5 plus 8, so we get 3i. Okay, subtracting is very similar. So we have 4 minus 5i minus 7 plus 8i. So that's going to be -3, and this is going to be minus 13i. Multiplying gets interesting. Let's see what happens. So we have 4 minus 5i times 7 plus 8i. That's 28 plus 32i minus 35i minus 40i squared. Remember, I squared is -1, so that becomes real. And we're going to get, as it becomes -1, and this becomes positive, so we get 68. And this is minus 3i. Okay, the next one, we're just dividing by 2, and that's going to be 4 minus 5i over 2. But if we want to write it in the form a plus bi, then this is 2 minus 5 over 2i. We often write it like this, and you'll see why later in the unit. But very important concept of complex numbers, the conjugates. So just like with conjugates of surds, one is one sign, like positive, the other one's negative. So this is how you denote it, with an asterisk or a line sometimes, but the IB uses this form. So let's see what happens when we multiply a complex number by its conjugate. We got a plus IB times a minus IB, and we get a squared minus IAB plus IAB, and then we get a minus b squared I squared. Remember, I squared is just -1, so we're going to have a squared plus b squared, and these cancel, so we just have a squared plus b squared. So notice this is just real. Okay, so if you multiply by a complex number by its conjugate, you get a real number, and that's going to be very important for some applications later on. Let's look at what happens when we have a conjugate of a conjugate. So the conjugate would be a minus bi, and if we do the conjugate of that, we get a plus bi. So the conjugate of a conjugate is just cancels each other out. You get the original complex number z. So some of these might be interesting. Let's see this one here. This is like negative a minus bi, and then we do the conjugate. So you're going to get negative a plus bi. And next we have the product of two complex numbers conjugate. So let's check that out. So let's do the product of two complex numbers, a plus bi times a, so we have to use a different letter for a different complex number, c plus di, and we'll conjugate all that. So this becomes ac plus adi plus bci plus bdi squared. And if we want to write this in the standard form, it's like minus bd from that. Plus, and we can write it as I times ad plus bc. Okay, next reciprocal conjugate. So let's take a look at that. So reciprocal conjugate of a complex number is this. If I want to do this, now you cannot do the conjugate right now because it's not in the form a plus bi, so you have to actually, let me write this out here. We have to get the denominator to be a real number. So we're going to multiply by the conjugate. And then we're going to get the conjugate of all that. So we have now on the numerator a minus bi. The denominator, remember from the previous page, we always get a squared plus b squared. Okay, so we can split that. We could split that into a over a squared plus b squared minus I times b, or actually let me write it like this, plus I times negative b over a squared plus b squared. Okay, so the conjugate of that is this just becomes positive, so we get a over a squared plus b squared plus I times b over a squared plus b squared. Okay, now if you think about the next one here, z star equals z if and only if. Let's check it out. Let's just represent z as a plus bi. So if we do the conjugate of that, actually let's just write it like this. Let's just write the conjugate of z. It would be a minus bi equals a plus bi. Oops, a plus bi. And we can subtract a from both sides, and then we can add this to the other side. We get 0 equals 2bi. That only works if b equals 0, okay? Or in other words, this only works if and only if z is real, okay? This implies it's a real number. Okay, here we have a sum of a couple complex numbers. Let me do that over here. It's not all that interesting though. So if you add two complex numbers, you're going to have a plus c plus I and b plus d. And if we conjugate that, then we just get a negative here. So it's not really all that interesting, I suppose. That should be a d right there. Okay. Next, let's multiply by the conjugate and see what happens. We already saw something above. So this will be the conjugate. And you should always get a squared plus b squared. You can work it all out to verify it. You should get a squared plus b squared. So that's going to be 25 plus 64. So you always get like a real number. We get 89 here. Next, now the conjugate of that is simply positive 5i. So that's going to be, now the I times I gives you negative 1. So the whole thing is going to be positive and get positive 25. Now that is a real number, but you can write it as a complex number. So, oops, that should be like an I right there. So the conjugate is 3 minus 0i, which equals 9. Alright, so to find quotients of complex numbers, you have to multiply by the conjugate of the denominator, very similar to surds, but even easier than surds. That should be the same. Okay, it's even easier than surds because this is always in the denominator is going to be a squared plus b squared, so it's going to be 49 plus 25. And a numerator, you're going to get 14 minus 10i minus 21i. That's going to be negative times negative is positive, but I times I is negative. So you're going to have negative 15. Okay, so we're going to get negative 1 minus 31i over 74 is the answer to that one. Now here you can multiply by the conjugate, negative 6i, but actually if you look at it, think about it, you just need to multiply by I, okay, because that will make it real in the denominator. So we multiply by I, we get 2i plus 3, right? I times I is negative 1. In the denominator we're going to get a negative. So to write in standard form, you can write this as negative half. Negative half minus, let me just double check something here. Yeah, negative half minus 1/3 I. Next one, you just split that into 2/9 minus 1/3 I, right? Now, let's do number 5 first, and then we'll go back to number 4. We can now use the quadratic formula and get complex roots. So let's use the quadratic formula. We get negative negative 4, which is 4 plus or minus root b squared minus 4ac over 2 times 1. So that's 4 plus or minus root, that all gives you negative 36 over 2, which equals, that's going to be 6i, right? 4 plus or minus 6i over 2, which equals 2 plus or minus 3i, okay? So this has no real roots, but has 2 complex roots. As a matter of fact, we say complex roots always come in conjugate pairs because of quadratic formula, basically, yeah. So if you get a 2 plus 3i, you always get a 2 minus 3i. They come in conjugate pairs. For number 4, so this works the same as with real numbers. You want to get the coefficients to match, and then you can solve simultaneously. So we have, in front of the z1, we got a 1 plus I here, and there's a 2 down here. So I'm going to multiply this one by 2, the whole equation, and this equation by 1 plus I, or sorry, yeah, 1 plus I, that's right. Okay, so I multiply everything by 2 here, and let's do the answer over here. That's going to be, let's leave it as 2 times 1 plus I z1. Now if you do, this is going to be just 2 times that, so it's going to be negative 2i z2 equals 3. And down here, same thing, 2, 1 plus I z1. And these are conjugates, right? So it's going to be a squared plus b squared is going to be 2. So that's going to be a plus 2 z2 equals, and on this side, actually if you look closely, that's going to be 3 times 1 minus I, 1 plus I, so we actually do have a conjugate here as well. Okay, so that is just going to be 2 right there, right? This whole thing right there. So let's subtract these equations, and this cancels, and we have negative 2i minus 2 z2 equals, and this is going to be, oh, I forgot to multiply the first equation by 2, if you notice. I had to multiply everything by 2. I should have probably written that in there. So that was a 6, and this is going to be 3 times 2 is 6, so you're going to get a 0 here. So that means z2 equals 0. And then we can get z1 by simply substituting into one of these equations, probably the second one, because if z2 is 0, that works out nicely, right? Yeah, so we're going to have 2z1 equals 3 minus 3i. So z1 equals 3 over 2 minus 3 over 2i. Okay, written in standard form. So you can solve simultaneous equations. You can get roots with complex numbers. You can do lots of arithmetic with complex numbers.